Okay, welcome back. In this class video, I'll be taking you guys current electricity. Okay, so I'll be taking you guys current electricity. Now, these are the aspects of current electricity I will take you guys. So we'll talk about electric drift velocity and a lot of things. Okay, so stick to the end of this video, okay, because I'll be showing you guys a lot of things, okay, under current electricity, as well as I'll be solving some exam based questions. Okay, so now let's start with current as a whole. What is current? I know that you guys have heard of the word current before. Okay, so now in physics, what is current? Okay, so now current just means current is the rate of flow of charge. Okay, so that is current for you. Rate of flow of charge. So that is just it. Or you can say the time rate of flow of charge. That is current for you. So current is represented by the symbol letter I. Okay. Yes. So this is current. Current is what? Current is the rate of flow of charge, right? So, or you can say the time rate of flow of charge. So that means that current is equals to charge over what? Over time. Okay. Yes. What is the SI unit of charge? SI unit of charge is coulomb. SI unit of time is seconds, right? So coulomb per seconds is the SI unit of what? Of current, which is also called ampere. Okay. So therefore, ampere is the SI unit of current. So current is the rate of flow of charge, right? So current is equals to charge over what? Charge over time. Okay. Yes. Now, in our previous class under electrostatics, I told you guys that charge is equals to what? The number of what? Number of electron, right? Yes, I told you guys that charge is equals to number of what? Number of electron. Where this one is number, why this one is, we can call this one, and we can also call this one charge, right? This symbol here, which is known as charge, is equals to 1.6 times 10 raised power minus 19. I told you guys in our very first class. Okay, yes. So we know that charge generally is equal to number of this symbol, right? Yes. So in a place of, okay, so just have this, just take this, just know this. Okay, very important. Okay, so we all know that current is equals to charge over time, right? Yes. Now if we make charge stand alone, let's say we cross multiply, charge will be what? Charge will be equals to what? Will be equals to current times what? Current times time, right? Yes. So you find that we have gotten two formula for charge. This one, right? And also this. Okay. Yes. So we'll make use of them soon. Now let's go to the next. So in summary to current is what? Current is the rate of flow of charge. The SI unit of current is ampere. Current is represented by this symbol. Current is equals to charge over what? Time, right? Yes. So charge is equals to this number times E. Then charge is still equals to what? Current times time, right? Yes. Okay. Then we'll move to the next part, which is electron drift velocity. Electron drift velocity. Now you may ask, what is electron drift velocity? Okay, so you see from the word electron drift velocity. Now, electron drift velocity is the average velocity. Okay, electron drift velocity is the average velocity of electron moving what? The average velocity of electron moving in a conductor. Okay, so that is electron drift velocity for you. Okay, the average. Okay, that is very important. The average velocity of electrons moving in a conductor. Okay, now in many exam based questions that we ask you, they say calculate. Look at this question. This question too. They said, okay, look at this question one. They said, where is the question? Because they said, find the drift velocity of what? Of the electrons. This is an exam based question. So this will tell you that electron drift velocity is very rampant in exam. Okay, yes, and look at this other one, drift velocity. So I will teach you. I will give you guys a formula to calculate for what? Electron drift velocity. So remember, so you guys, the electron drift velocity is what? Is the average velocity of electrons. The average velocity of electron moving what? In a conductor. Now, how are we going to get this how are we going to get this velocity? How are we going to get the formula? Okay, because once we get the formula, we use the formula to solve these two questions. How are we going to get it? Now, there's one quantity we know known as electron density. There's a quantity known as what? Electron density. Okay, we are going to use this quantity to get electron drift velocity. So electron density. Okay, electron density is represented by what? Remember, we want to use electron density to get what? To get an electron drift velocity. Okay. Now, what is electron density? Electron density is represented by what? It's represented by this symbol n. Electron density just which is represented by n is equals to what? The number of free electron per unit volume. Okay. The electron density, which is represented by small letter n, is equals to what? N. This n is known as what? Numbers of free electron, right? Yes. Divide by what? Divide by volume in the conductor. Okay, so electron density is just the number. Just look at, let's say it's a conductor. Now the numbers of electron in a particular per unit volume in a conductor is known as what? Electron density, right? Yes. So electron density is equals to numbers n over what? V, right? This n is what? Is numbers of what? Numbers of electron, right? Very important. Number of free electrons. Okay, number of free electrons. Why this one is what? Is volume. Okay. Yes. Remember, we want to use one to get electron drift velocity. Now let's continue. Now, if you look now, let's go now. If you look at it, n is equals to what? Electron density is equals to numbers of free electrons by what? Volume, right? Yes. Now let's go back to this formula. Here we see charge is equals to what? Numbers of what? Numbers of free electron times E, right? Yes. Now let's go back to this place. Charge is equals to Ne, right? Yes. But remember, charge is still equals to what? Current times time, right? So whenever we see charge here, we'll put what? We'll put IT, right? Current times what? Time, right? IT. Okay, we want to make n stand alone so that whenever n equals to here, we'll place it here. I don't know if you understand. So we'll make n stand alone, divide both sides by what? Charge, right? Which divide both sides by E. So we'll cancel this. Therefore, we all know that numbers of free electrons is equals to what? IT over what? E. So whenever we see n, we'll put what? IT over E. So IT, then divide by what? E, then plus this volume, right? Yes. Now what next? We find, so from this we find out that electron density is equals to what? Current times time divided by what? Charge of electron times what? Times volume, right? Yes. Charge of electron times what? Volume. Okay. So now remember, what are we looking for? We're looking for what? Electron drift velocity. We're looking for velocity, right? Remember, this is volume. Now I told you guys, normally we all know that volume. What is volume? Volume is what? Volume can be equals to what? Area times what? Area times length, right? Can be area times length, or you can say volume is what? Length times breadth times height, or you can say area times length, right? Yeah, so you can still say what? Length we can use distance in place of what? Length, right? Can use distance in place of what? Length, right? So you can say volume is equals to area times what? Distance, right? It's very correct. Okay, you can use length in place of distance, you can use distance in place of length. So you can say volume is equals to what? Area times distance, right? So therefore we say, okay, V, which is volume, is equals to what? Area times distance, right? Yes. So whenever we see V here, we'll put what? AD, right? So we'll put area times what? Distance, right? Yes. Now, this is current, this is time. We want to let's make current stand alone, okay? We want to get velocity, so let's make current stand alone, cross multiply, right? So IT will be equals to, okay, so IT will be equals to what? Ne, this n multiplying the charge of electron times A and D times AD, right? Yes. Now we want to make current stand alone, divide both side by T, right? Divide both side by T. So this one will cancel this. Therefore, current is equals to what? Current is equals to this small letter n is known as what? Electron density. Please don't mistake it with numbers of free electron. Okay. Yes. So current is equals to electron density, charge of electron, area, distance of our time, right? Now before I forget, okay, we are good to go. Okay, let's continue. Okay, so now what next? We want to get velocity now. If you look at this, NEAD divided by T. Now, this same thing, still same thing as, you know that this this T can also means that can also be something like this, D over T. I don't even understand. Okay, so I will tell you guys something. Now, D over T here will give us what? Remember, velocity. What is velocity? Velocity is what displacement over time, right? Or you can say D over T, right? Yes. But if you look at this place here, D over T will give us what? Will give us velocity, right? Yes. Remember, we landed something like this. We landed something like this, right? Yes. So this D now divide this T will give us velocity, right? Yes. So in the place of D over T, we put what? We put velocity. So therefore, all here will not be what? All here will not be V, right? All here will not be V. So therefore, current is equals to NEAV, right? Now, what I will remember with this velocity is our what? Is our electron drift velocity. Now, I want to make it stand alone by dividing both sides by what? NEA, right? Dividing both sides by NEA. So this one will cancel this. So therefore, electron drift velocity is equal to the current over what? Current passing through that conductor over the any electron density times the charge of electron times what the area of the conductor. Okay, so let's do it together. One, which is so therefore, yeah, NEA, right? So this is the formula for what? This is the formula for electron drift velocity. Okay, so now let's solve this. Let's use the formula to solve these two questions. Okay, so please take note of all these things. Okay, so the things I will tell you to take note of. Okay, yeah, take note of the formula of current. Right, current is Q over T. Then take note of this. We all know that charge, if you cross multiply, charge equals to current times time. Apart from that one, charge is equals to number of electron times the charge of electron. Right, so take note of this one. Take note of this. Then take note of electron density. Remember, it's small letter n. It's different from it is different from what? Numbers of free electron, right? Yeah. So take note of this one. Then take note of this, right? So now let me clean this place. All right. So now let's solve the first question. It's very easy to solve. Okay. So it's very easy. Now let's do the question. It said a copper wire of area 3 times 10 to the minus 6 meter square carries a current of 10 ampere. So the current is what? Is 10 ampere. Our area is what? Our area is 3 times 10 to the minus minus 6 meter square. Okay. Then assuming that each copper atom contributes one free electron to the metal, find what? The drift velocity of the electron, right? So we're looking for electron drift velocity, right? Okay. Yeah, find the drift velocity of the electron. In this wire, they gave us density of copper. They gave us Avogadro's number. They gave us the density of copper, right? This is density of copper. They gave us Avogadro's number to be this. They gave us the mass of copper to be this. They gave us this charge of electron, right? Yes. Now, they still look for electron drift velocity. Very simple. Okay, go to the formula. Electron drift velocity is equals to what? Current over what? Electron density, right? Times the charge of electron, then times what? Area. So let's continue. Current is what? Current is 10 ampere, right? Then what about, did they give us N? Yes, they gave us N indirectly. Now what is N generally? I told you guys that N is equals to what? N is equals to this. N is what? Electron density, right? And what is electron density? Electron density is the number of free electron divided by what? Volume, right? Divided by what? Volume, right? Yes. Now these numbers of free electron is still something as what? It's still something as Avogadro's number. Okay, now where is Avogadro's number? Avogadro's number is what? 6.02 times 10 to the power 23, right? Then divide by volume. Now, in this question, did they give us volume? No. But we can get volume. How are we going to get volume? If you look at the question, they gave us density of copper. They gave us mass of copper. So we're going to use density and mass to get volume. How? Remember, density of a substance is equal to the mass over what? The volume of that substance, right? So they give us the density, they give us the mass, so we use it to get what? Volume. So let's do it. So where the density of copper is what? 8.95, right? Then the mass of copper is what? 63.5, right? So let's look for volume. Okay, so if we make volume stand alone, from that formula, if we make volume stand alone, we have something like this. V is equals to M over D, right? So M is what? The mass of copper is what? 63.5. Then the density of copper is what? Is 8.95. So let's divide both of them. If we divide both of them, so 63.5, right? Then divide by 8.95. So when do I got 7.09, or we can say 7.1. So the volume is what? The volume is what? 7.1, right? 7.1. Now let's divide these two to get n. Once you get n, put n here, right? So let's do it. So 6.02 times 10 raised to the power of 23, then divide by what? Divide by 7.1, right? Divide by 7.1. I'm coming. Divide by 7.1. My answer here is 8.47 times 10 raised to the power 22. 8.47. So n is what? N is what? 8.47 times 10 raised by what? Times 10 raised to the power of what? 22. Okay. Then charge of electron is what? Charge of electron, we know charge of electron is 1.6 times 10 raised to the power minus 19, right? Then times area. Area is what? In the question, area is what? 3 times 10 raised to what? 3 times 10 raised to minus 6, right? 3 times 10 raised to the power minus 6. So let's do it together. Let's do everything together, okay? So let's do everything together. So 10, which is the current, divided by what? Divided by 8.47 times 10 raised to the power of 22. Then times 1.6 times 10 raised to the power of minus 19. Then times 3 times 10 raised to the power of what? Minus 6. Minus 6. So my answer here is 200 is 245.9. Okay, it's 245.9. All right, so that is our answer. So the electron, I'm coming. Okay, so all right, I want to check something. Okay, we do everything correctly. All right, so the electron drift velocity is 245.9. We can just say 246 meter per seconds. Okay, so the electron drift velocity is what? 246 meter per second. The electron drift velocity is what? 246 meter per seconds. Okay, yes, so this is actually correct. Okay, 246 meter per seconds. Okay, yeah, it's actually correct. Okay, but in the question 8.95, in the question, the density was given in gram per cm cube, gram per centimeter cube. So we need to convert that centimeter cube to meter cube. Okay, so we need to convert. Remember, the density was in centimeter cube. Okay, yes. So remember, when we're looking for the density, and when we're looking for the volume, finally the volume equals to the mass over the density, right? The mass was the mass of copper was 3.5, right? Yes. Then the density is 8.95. Okay, in the question it was given in gram per. The density was in centimeter cube and not in meter cube. Okay, so what I'm going to do here, it's very easy. Okay, so let's convert this 8.95 gram per this centimeter cube to what? To gram per meter cube. How good to do that? By dividing by 1 million. Okay, that is just it. Okay, now let me tell you. Now remember, if you want to convert centimeter to meter, what are we going to do? We divide by what? 100, right? Yes. So we divide by 100, divide by 100, by 100, right? Yes. What about if we want to convert centimeter square to meter square? We divide by what? So now be times 2 of this 100. When that is times 2 of 100. That is 100 times 100. That is what? That will be 10,000, right? 10, no, right? In the year, it will be 10,000, right? So if you want to convert from centimeter cube to meter cube, we divide by what? 10,000, right? I mean, centimeter square to meter square, divide by 10,000. Remember, if you want to convert from centimeter to meter, divide by 100. Then if you want to convert from centimeter square, that is 100 times 100, right? We divide by 10,000, right? Yes. Then what about when you convert from centimeter cube to meter cube? We now divide by what? We now divide by 1 million. That is 100 times 100 times 100. 100 times 100 times 100. That is what? 1 million. Okay, so that is 100. Look at it, times 100 times 100. That is what? 1 million, right? Yes. So if we want to convert from centimeter cube to meter cube, we divide by what? 1 million. Hope is clear. From centimeter to meter, you divide by 100. Then if from centimeter to meter we divide by 100, if you look at this centimeter cube, that is, if I want to convert centimeter cube to meter cube, you now divide by what? Still look at the square. You now take this, you now divide by what? 100 square is what? Is 10,000, right? Yes, look at this other one, cm cube. If you convert from cm to meter to by 100, then this one will be 100 cube, right? Which is 1 million. So to convert from centimeter cube to meter cube is what? Divided by what? 1 million, right? Yes. So if we convert this now, so that is just it. So if we want to convert this one now, 8.95 gram per so yeah, if I want to convert this one now, 8.95 um okay, I'm coming. Yes. So let's just this is the answer, right? Because this one 246, right? Yes. So we divide by what? We divide by 1 million. If we divide by 1 million, we get the actual answer now. 246 divided by 1 million. So you get the right answer. Okay. Our answer will now be 1, 2, 3, 4. Now it will now be 2.46 times 10 is what minus 4. So that's just it, okay? So the answer, let's not just waste our time here. So since we got this one, then I want to convert it to what? To yeah, we divide. We want to convert cm to meter cube. Divide by 1 million, right? So let's divide our answer by what? By 1 million. So divide our answer by 1 million, we get something like this. We have our answer will now be 0.000 246, right? Yes. Now, which is same as what? Let's turn to standard form. 1, 2, 3, 4, right? So it might be something like this. Now something like this, 2.46 times 10 raised to the power minus 4, right? So this is our velocity. Okay, yes. So that is just it. Take note that the process you followed, they are all correct, right? Yes, just that I didn't complete the full question. The density was in gram per cm cube. So convert that cm cube to what? To meter cube, that dividing by what? 1 million, right? So that is just it. So yes, we are done. Now let's move to the next question, question 2. Okay, so we are still dealing with electron drift velocity. Okay, we are still dealing with electron drift velocity. Okay, so now question 2, they say a conductor material has a free electron density of 10 raised to the power 24 electrons per a meter square. Now, my meter cube rather. Now this electron density, right? They give us electron density to do what? To be 10 raised to the power 24, right? Yes. Now let's continue. When a voltage is applied, a constant drift velocity of, now they give us drift velocity to do what? The drift velocity of 1.5 times 10 to the power minus 2, right? 1.5 times 10 to the power minus 2 meter per second, right? Yes. Then, okay, a constant drift velocity of 1.5 times 10 to the power minus 2 meters per second is attained by the electron. If the cross-sectional area is what? They give us the area to be what? The area is 1 centimeter square, right? Yes, calculate the current. We are looking for current. We are looking for current. We don't remember charge of electron is what? 1.6 times 10 is what? Minus 19. So it's very easy. How are we going to do it? This is the formula. We are looking for what? I, right? So we all know that drift velocity is equals to current over what? Electron density times charge of electron times area. So just cross multiply. Current will be equals to what? The drift velocity multiplying n a then a, right? So let us multiply everything straight. Drift velocity is what? 1.5 times 10 to the minus 2, right? Then and current and electron density is what? Is 10 to the power 24, right? Charge of electron is 1.6 times 10 to the power minus 19, right? Then the area is 1 centimeter cube. We need to convert it to, centimeter square. We need to convert it to what? Meter square. How are we going to do it? Remember, to convert from centimeter to meter, we divide by what? 100. Then to convert from centimeter square to what? To meter square, divide by what? 100 square is what? 1,000. It's 10,000, and so divide by what? 10,000. So divide this. So let's divide this one by 1 divide 10,000. So let's do it. 1 divide 10,000. 1 divide 10,000. So 0.001, right? So the area is what? 0.0001. So let's multiply everything to get our current. So if we multiply everything, get our current. So 1.5 times 10 raised to the power of minus 2, then times 10 raised to the power of 24, then times 1.6 times 10 raised to the power of minus 19, then times 0.0001. So the answer is 0.24. So our current is what? 0.24 ampere. 0.24 ampere. So this is it. So just take note, just know electron drift velocity Yeah, there's usually exam-based questions, right? So take note of it, how I derive it, take note of the formula, and all. Okay, now let's move to the next part, which is current density. Okay, current density. So current density. Now, what is current density? Okay, so it's very easy. Now, current density, you have done this, done this. Now, current density is represented by symbol J. Okay, it is a vector quantity. It is okay. Current density is current per area. That is just it. Current per area. That is current density for you. Is current per area. I'm coming. G velocity was 1 over n. I mean current over what? NEA, right? Yes. So now current density is represented by the symbol J is equal to current per area, right? Yes. So now, if okay, now if this is current, right? That is current is represented by that is I over what area, right? Yes. Now, remember from drift velocity. This one, I want to give you guys another formula. Again, this is another formula under current density. Now, from drift velocity, we found out that drift velocity, electron drift velocity is equal to current divided by what? Electron density times the charge of electron times what? Area, right? Because multiply, we find out that current will be equal to what? Because to the velocity, drift velocity, multiplying the electron density, then multiplying charge of electron times A, right? Yes. So in the place wherever, so in this place, so we'll put in place of I, we'll put these values here. I'm gonna put this letters here, right? So J will be equal to what is I? I is what V N E A, right? Then don't forget about this A. Now where is common? A, divide this, cancel them, right? Therefore, um, therefore current density is equals to what? You can say it's equals to VNA, or you can say NEV. Okay, yeah. So this is the formula to calculate for what? For current density. So this, remember, N is what? Is electron density, right? Is electron density. And what is electron density? I've told you guys is your number of electrons divided by what? Volume, right? Electron density is what? Is small letter N, right? This one is number of electrons divided by what? Volume, right? Yeah, so that is it. Now let's enter the next part. Arrangement of cells. Okay, arrangement of cells. Okay, so please take note of all these formulas. Okay, then one more thing. Current current density is a vector quantity. It's different from current. Current is a scalar, whereas current density is a vector quantity. Okay, so now let's move to the next part, which is arrangement of cells. Okay, now what is cell? Okay, this is not cell in biology. Okay, so cell, or you can say electrical cell. Okay, cell is a device that converts chemical energy into electrical energy. Okay, so a cell is a device that converts what? Chemical energy into electrical energy. Now, what is the difference between cell and a battery? Now, cell and the battery, they are basically the same thing, but not that the same. Okay, battery is just a collections of what? Cells. When there are two or more cells, you get a battery. Okay, so that is just the difference between a cell and a battery. A cell is a device that converts uh, chemical energy into electrical energy. Same goes for a battery, a device that converts chemical energy into electrical energy. Now, a battery is made up of many cells, or as you can say, made up of multiple cell collection of cells. Okay, yes, that is important. So now let's talk. Now, the important thing about in this part is the arrangement of cells. Okay, yes. Now there are two arrangements of cells. Okay, so there are two arrangements of cells. Okay, there are two arrangements. Okay, now before then, now how do we represent cell? We represent cell like this. Okay, we represent cell or battery like this. Okay, yeah. So this is how we represent cell or battery. One, this long, please, very important. This long terminal is known as the positive terminal. Very important. Known as the positive terminal. Okay, positive terminal. While this small this one is known as a negative terminal, negative or terminal of a cell. Okay, negative terminal of a cell. If you see something like this, you have seen it in a DC circuit. Something like this, you know that this is cell. Okay, cell produce what? Voltage, right? Yes. Cell produce current, right? Yes. Produce current. Okay, the one that drive current it drives current, or you can say it pumps current in a circuit. Okay, so this is a cell. Okay, this long one is a positive terminal. This short one is what is the negative terminal of a cell. Okay, so there are two arrangements of cell. We have the series arrangement. Okay, we have the series arrangement, and we have series arrangement. Then we have the parallel arrangement. Okay, we have the parallel arrangement. So now on that series, very easy. Okay, so So the EMF of a cell, now under series, okay, then under parallel. Now under series, now how do you know a series connection of cell and how do you know parallel connection of cell? It's very easy. So for a series connection of cell, we have something like this. Okay, I've told you guys how do you know series, right? They are connected. This is a series connection of cell, right? Now what about parallel connection of cells? So it will be something like this. Okay, it will be something like this. Okay, I'm coming. Okay, it will be something like this. Look at it. Find that this is a parallel. How do you know a parallel? Now I've told you guys earlier then our previous class. I told you guys that in our last two class or so. Now how do you know a parallel? How do you know parallel and series? Now for series, they are connected by just one. Should I say wire? Okay, they are connected by one single wire. Okay, let's use wire in this place. Okay, they are connected by one single wire. But in a parallel, you find that in parallel, there's usually a division. Whenever you see yes, where one particular wire divide, you know that oh, this is what parallel. In series, they are connected by just they have the same connection, right? But in parallel, the cells they have different connection. There must be division. Look where there's a division. Look at it, this one single thing divided into three. So you know so that is telling you that this cell, they are all parallel to each other. Okay, so that's how you know a parallel from a series. So that's how you know series and parallel. You can call this one cell one, cell two, which is okay, three, four. Okay, so that'll be E1, E2, E3, right? Yes, okay. Now, in series arrangement, to calculate the total EMF, this E is the EMF, that is the electromotive force, okay, of the cell. Okay, now, this is a cell, this is a particular cell, it's on that cell, it's on that cell. Okay, now, apart from that one, each cell has, remember, like what I told you guys, cells a device that converts chemical energy into electrical energy, and they produce current, right? Yes. So now each particular cells they also have an internal resistance. Internal resistance, there's this thing inside a cell that oppose the production of current in the cell. So that is internal resistance, right? So each cell have their own internal resistance. So this first cell, this is the EMF for the first cell, right? Then this will be the internal resistance, that is R1. Then for this second cell to be R2, third cell R3, the fourth cell R4. So this one will be R1, R2, R3, right? Yes. So if we want to talk about the EMF of a cell, we need to also talk about the internal resistance of the cell, right? Yes. So the EMF is that force, which is known as electromotive force, is the work done in moving. Yeah, it's more than a moving charge in an opposite circuit. Okay, or you can simply say yeah, the electromotive force of a cell is that force that drives current in a what? In a circuit. Okay, that force. Okay, yes, which can also be regarded as voltage. Okay, yes, but they're kind of different. Now let's focus here. Okay, arrangement of the cell, series arrangement, parallel arrangement. Now, how do you arrange? How do you the total now to calculate the total EMF in a series in a series arrangement is very easy. You say total EMF is equals to what? Is equals to the EMF due to the first cell plus the EMF due to the second cell plus the EMF due to the third cell plus the EMF due to the fourth cell, depending on the number of cell. Now, what about the total resistance? It's still the same thing under series. The total resistance will be equals to resistance of in the first cell plus resistance in the second cell plus resistance in the third cell plus resistance in the fourth cell, right? Yes. So this is under series. Okay. Yes. Now, there's still one thing I want to tell you guys. This is the normal arrangement of a cell. If you look at it, find out that this is the positive terminal, negative terminal, positive terminal, negative, positive terminal, negative, positive terminal, negative, right? Yes. Now, this it does not. Now there are certain questions where the connection will be opposite. Now let me give you guys some particular example. Okay. Now something like this. I'm coming. Something like this. Okay. Okay, we have something like this. So this is one, set two, set three, set four. So E1, E2, E3, E4. Okay. Now, if you look at this one, look at it. This is normal arrangement of cells in series, right? The positive terminal first, negative terminal, then positive, negative. If you look at this one, in this arrangement, this is abnormal arrangement, right? Look at this third one. Find out that The third one, the negative terminal is connected to the negative terminal of the second time of the second cell, right? Now in this type of scenario, how do you calculate for the total EMF? It's still easy, okay? Now you find that it is this third cell that is wrongly connected, right? So how do you calculate for the total EMF in this type of scenario? This to calculate the total EMF, this one it might be something like this. Total EMF is equals to now you will add all the cells that are connected correctly. Then you minus let's just now which cells, how many of the cells are connected correctly? This one, and this, right? So we add them together. E1 plus E2, then plus what? E4, right? Now what about this other one? You now subtract from what? E3, the one that is wrongly connected. Okay, so that's how you calculate the total EMF when the cells are not connected rightly. Okay, yes. So the one that is not connected correctly, you will add all of them that are connected correctly. Then you subtract it from what? From the line that is not connected correctly. So that is just it. Okay. What if there are two cells that are not connected correctly? Let's say this other one now. Something like this. Let's say I have something like this. So I have something like this. Negative terminal connected to negative terminal. So in this scenario, we now minus. We now still okay. We now add these two together. E2 plus E3. We minus it from these two that are correct, that are connected correctly. Okay, so something like that. Okay. So just take note that in case they give you a particular question like this, just make sure you check each of the cells if they are connected correctly. How do you know if they are connected correctly? The negative terminal of one is connected to the positive terminal of the other one. Negative terminal of the other one is connected to the positive terminal. So it's negative to positive. Look at it. Right? Yes. So that is it. Now what about so in summary, under series connection or under series arrangement, to calculate for the total EMF is equal to E1 plus E2 plus E3. It depends on the number of cells. If there are 10 cells in this place, we do it up to what? E10, right? Yes. Same goes to the resistor. We do it up to what? R10. So this is it's okay for so this is formula to calculate for the total EMF of a cell of cells that are connected in series. Then this is formula can calculate for total resistance of cells that are connected in series. Now about for parallel, now be opposite. Okay, for cells that are connected in parallel, this I've told you guys how you know parallel, right? Yes. Now for cells that are connected in parallel, the total EMF will now be something like this. Okay, total EMF will now be something like this. Okay, now I want to tell you guys something. Now for cells that are connected in parallel, this is very important. The total EMF now, for cells that are connected in parallel, if all the cells are similar, let's say E1, E2, and E3, they are equal, they have equal EMF. If all the cells are similar, that is, they have equal EMF. The total EMF of this arrangement will be equal to what? Will be equal to the EMF of one of them. I don't know if you understand. Now, let's say, for example, E1, the EMF is 2, E2, the EMF is still 2, then E3, the EMF is still what? Is still 2. That is all the three cells that are similar, right? Yes. Now what will be total EMF? The total EMF will be equal to what? The EMF of one of them, which is what? One of them, any one of them will be EMF in this scenario will be what? Will be 2. You understand? So if they give you a particular question and it says they are connected in parallel and they are similar, you don't need to stress yourself. So you calculate total EMF. You don't need to stress yourself. Just say the total EMF is equal to what? EMF of any one of the cells. So since all of the cells are equal, just the EMF will be equal to what? EMF of one of the cells, right? Simple. That's just it. Then, but for to calculate your total resistance will not be what? 1 over rho to 1 over rho total equals to what? 1 over rho 1 plus 1 over rho 2 plus what? 1 over rho 3, right? Yeah. So this is it. This is formula to calculate for the total resistance of the cells when they are connected in parallel. But when they are now, yes, so that is it. Then the formula to calculate um for the total EMF of the cell when they are connected in parallel, if the cells are equal, that is if the cells have equal EMF, don't need to stress yourself. The total EMF equals to 2. But let me give you the formula generally. To calculate for the EMF of a cell when they are connected in parallel, something like this: 1 over E1 plus 1 over E2 plus 1 over E3. That when each cells they have the same when it says when each cells that are connected in parallel, let's say they have the same EMF, just know that the EMF of one of them is the EMF, the total EMF is equal to the EMF of one of them. Okay, so that is just it. Okay, so just take note. So that is for parallel. If let me repeat myself. To calculate total EMF of cells that are connected in parallel, if the cells are all similar, the total EMF is equal to the EMF of one of them, right? Yes, which is what? Which is in this scenario, let's say we use which is 2, right? Yes. But what about the total? What about to calculate the total resistance? Is 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so that's just it. Then what about if the cells are not similar? If the EMF of what about if the cells are not similar? That is, if the EMF are not the same. Now, which formula are we going to use? Now, if the cells are not similar, that is a complex DC circuit. Okay, so to solve such a question, so to solve the EMF, we make use of Kirchhoff rule. Okay, so which will be in another class video. Okay, so that is just it. So the sort of summary of arrangement of cells. Now, when cells there are two arrangement of cells, series arrangement and parallel arrangement. Under series arrangement, this series arrangement, total EMF is equal to what? E1 plus E2 plus E3 and so on. While their total resistance is equal to R1 plus R2 plus R3 and so on. Then for parallel, to calculate for the total EMF of for parallel, if all the cells are equal, the total EMF is equal to what? EMF of one of them, right? Yes. Then to worry about their total resistance, the total resistance is what? 1 over R1 plus 1 over R2, 1 over R3. Now, what if when the cells are not equal? What if the cells are not equal? This formula will not work. All these things will not work. Well, if the cells are not equal or if they are not similar, to calculate their EMF, we make use of Kirchhoff rule. Okay, yes, you can get this thing, the EMF using Kirchhoff rule, which will be treated in another class video. Okay, so we are done with arrangement of cell. Okay, then let's move to Ohm's law and resistance.